we now prove the more general form of the chain rule. That is, you'll remember that last time we assumed that g of x did not equal g of c for all x's near c. Now we'll take away that supposition and prove the theorem in a different fashion. This proof's a little more complicated, as you can imagine. You recall what the theorem said, that the derivative of a composition is equal to f prime of g of x times g prime of x. So here's how we do it. We fix x and define a new function eta of delta x. That's the Greek letter eta. And it's equal to the following. It's 0 if delta x equals 0, and it's delta y over delta x minus f prime of x if delta x does not equal 0. Now notice that the limit as delta x approaches 0 of eta of delta x is the limit of that expression there, which equals 0. Hence, eta is continuous at 0. Okay, also notice that because delta y equals 0 when delta x equals 0, we have delta y equals delta x times eta delta x plus delta x times f prime of x. And if you let delta u equal g of x plus delta x minus g of x, you observe the following. The limit as delta x approaches 0 of delta u equals the limit of that difference in the g values as delta x approaches 0. That, of course, equals 0. In other words, the limit of eta of delta u as delta x approaches 0 equals 0. Okay, good. Finally, let's look at delta y. It's equal to delta u times eta of delta u plus delta u times f prime of u. Okay, divide by delta x. So delta y over delta x is delta u over delta x, eta of delta u, plus delta u over delta x times f prime of u, assuming that delta x does not equal 0. All right, we're almost home. What is dy dx now? Well, it's du dx times the limit of delta x goes to 0 of eta of delta u plus du dx times f prime of u. Well, this first expression we showed was equal to 0. So that's du dx times 0, and here we have du dx times f prime of u. So dy dx is nothing more than du dx times f prime of u, which is du dx times dy du, or if you want to flip them around, dy du times du dx. That's precisely the chain rule.